Hello, everyone. Welcome back to the Union hosted talks. We usually do workshops for this, but we're switching it up a little bit. I'm Niels Bantilan. I'm the chief ML engineer at Union, and today I just wanted to go through a interesting take that we've had kind of recently. Rebuilding Flight into a new V2 that we've been talking about for a while. But I kind of want to take a step back and present this in terms of async Python. Talking about container-enabled async I/O is all you need to build Pythonic AI workflows. The all you need meme is interesting and fun. I love further qualifying it so that it's not this all-encompassing statement. So this is going to be roughly an hour conversation, or not a conversation, a lecture really. I'll take you through some of my thoughts here and our take on how to build durable and robust AI workflows, taking a lens kind of through the ages. So talking about it in terms of the current state of AI and LLMs and agents and all that stuff. Taking it also back to machine learning, training machine learning models in a classical sense as well, with random forests and logistic regressions and all that good stuff, and deep learning as well, of course. And then also taking it even further back to data, doing data ETL and processing data. And these are all interrelated stacks at this point. And so without further ado, let's get started. So if you're in this bucket of people who have built some kind of agent thing, congrats, or maybe congrats to you in the future if you ever build this at some point in your career. Typically, when we build these kinds of systems out, when we're just getting started, we're getting a handle on things, we're building demos, proof of concepts. The things you typically do is you might start relatively small, right? You might start with one or maybe a couple of LLM providers to test them out. Maybe you have a router that routes to different providers based on the task that you're dealing with at a time. You may have tools or retrieval tasks that the agent performs, fanning out to maybe a couple of hundred different tasks. You have maybe 10 tools that the agent is having to manage and figure out what to use. And so on your laptop with 10 different inputs, this works beautifully. But in production, if you have long horizon agents, background agents that just kind of run perpetually or on a schedule, and when you scale things up to 10,000, 100,000, a million inputs, then things start to fall over when you hit real rate limits. Connections pile up. One slow connection stalls a whole batch. You get an out of memory on a tool call that is doing some compute-heavy, compute-bound work and kills the entire flow. You can't add backpressure to inbound work without rewriting your fundamental core logic. Or maybe you're using a framework where you can't actually even customize this production level stuff. Or maybe you build an ML workflow, right? And I'm not going to go through all of these, but the point here is that you encounter very similar things actually in traditional ML workflows, where you start building stuff out on a laptop, you take it to production, things scale up, and things start to break. Obviously, agents are slightly different, and there are some important differences with the workload styles and the workload profile. But at least in practice and things that I've built throughout my career and currently, there are very similar shapes to certain things that come up in production. Or maybe, you're writing an ETL workflow, and maybe, 5 to 10 years ago, things were a little simpler, maybe. The stack wasn't as inundated with all sorts of technology choices. But especially nowadays, data ETL services a lot of different things. It's not only analytics and reporting. It's also, maybe forecasting, model building on tabular data. Maybe it's even multimodal data. Maybe you're supporting ETL workflows for machine learning and deep learning and multimodal stuff, even AI agents, right? RAG you can think of as a retrieval augmented generation as the previous. There's a prior step to actually running the full pipeline, which is to reconstitute the vector database or whatever system you're using for retrieval. So as these different concerns and different stacks mature and start to interrelate and interconnect with each other, a lot of the patterns that I see among Union customers, Flight open source users, I'll get to Union and Flight later, orchestration issues, runtime issues start to compound. And at least for me, I've seen certain patterns that keep coming up in solutions and design patterns that kind of help somewhat across the board. And so you hit these things and then you reach for a framework, right? You reach for a workflow DSL, something you write in YAML maybe, something you might write in a language like Python or JavaScript that has a special syntax or is a subset of that language that you'll have to learn a little bit how to use. And the thinking here is that Python isn't enough to express the ideas that we need to solve our orchestration and our production grade AI ML workflow problems. And this is the instinct I want to push back on in this particular talk. And so the core reframe here is somewhat technical, and somewhat obvious, right? This is not super groundbreaking, but we can think of production AI workflows as dynamic execution graph of waits, where waits are things that you are literally waiting on. So you can think of Python Asyncio awaits, or in JavaScript there are, and many other programming languages, there are the equivalents. But you basically have a bunch of nodes, so it still is a graph, but unlike the previous generation of systems where you know the shape of the graph beforehand, we live in a world of agents, where agents do data science and agents do machine learning and they do many other things, where you don't know the shape of the graph beforehand because it depends on inputs or intermediary outputs that are yet to be computed. Workloads vary in terms of concurrency, parallelism, backpressure requirements, and they are composed of potentially variable compute units. So some of the nodes in there might be CPUs of varying sizes and with different GPU accelerators in them, or with different memory requirements. And one piece of this talk is that the Asyncio standard library in Python actually fulfills these first two requirements. Python itself plus Asyncio, which allows for concurrent programming. By the way, I'm going to mention Python here a lot, but this really applies to many different programming languages that you might be using. For that third problem, though, the heterogeneous variability in compute in a particular execution graph, you're going to need a different solution, right? You also, as a kind of a byproduct or a corollary to this, you also want some way of isolating nodes so that breaking one node will not break the rest of the pipeline, and you can easily kind of recover from a particular run that has failed so that you don't have to recompute all the previous steps, right? So you want some way of containing the blast radius of a particular failure, in this case, calling out of memories. And And as I mentioned, as I alluded to, isolation isn't just around this type of like kill error. This is also just isolation of compute around permissions as well, right? So you may not need database access across the entire, let's say, machine learning pipeline or data pipeline, right? You may just need permissions on one of the early nodes that reads in data, and then the rest of the pipeline doesn't really need that. And this kind of just from also a security angle reduces the surface area of attack, where if you have a long-running process, some attacker can't just go into the training part and access all of your keys that was needed in a prior step. So to solve these problems, you need an actual container orchestrator that plays well with Python. And this is a loaded, overloaded term. Here I mean something like Kubernetes, right? So you have containers like Docker containers, and a way for you to spin them up, spin them down. Also a way for the containers to pass data across the different ones, right? So you'll have on any given application, multiple steps. Each step could happen in a different container each. So you'll need a way to move data between them. And so the claims I'll make, just to reiterate, are that async IO should be one of the main tools you reach for when building production AI workflows. These require concurrency, parallelism, managing cancellation and tearing down of various infrastructure pieces, backpressure, etc. And when you need scale and strong isolation, async IO is not something you discard. It stays in your toolkit while you add a container orchestrator that schedules containers on the right compute. And so you're still writing Python in async to express the logic and data flow of your program. It's just that now, as we'll see later in some of the slides and demos I'll show, you write in Python, but under the hood, there is some system at the infrastructure level kind of coordinating and orchestrating all the containers you need, getting all the data flow right so that it feels like you're still kind of programming in Python. So for the rest of this, I'm going to go through sort of a deeper dive on what I mean by production AI as a graph of weights. Talk about in a little bit more detail these three coordination stories across like AI agents, ML, and data ETL. I'll also then go into a quick crash course on async Python. Again, I am very much focused on Python in this particular talk. But as I said earlier, there are equivalent constructs in any programming language that has concurrent programming. I'm just kind of anchoring it to this. So we'll dive into some Python-specific constructs around async programming. I'll then talk about the second piece of this, which is containers, using containers as an isolation boundary. And then just go through a case study, just a few examples, Flight as an open source reference implementation for some of these ideas. I'll wrap up with a sort of what you can do tomorrow to implement some of these ideas. Okay, so as I said earlier, right, agentic workflows have certain characteristics. You have a session with an agent that may have many round trips. It does retrieval tool calls, a bunch of other things. It may even have a human in the loop. In classical ML, you have many steps around training, batch inference, hyperparameter optimization, right-sizing compute for each of these pieces. You want to optimize model throughput and fair resource sharing so that one job isn't hogging all of the resources. And all of these, especially now where we have like RL post-training workloads that are not as simple as this classical ML setup, where you actually have inference kind of in the loop doing rollouts for your agent, your RL agent. this kind of setup gets even more complicated. And with ETL, even with these kinds of workloads, you have patterns like I/O fan out, backpressure, so that you're not sending too many jobs into the queue, processing large amounts of data. So you don't, you want some kind of concurrency here, so you're not sequentially looping through batches of your data or partitions of your data. And so you have the coordination piece, you have the coordination problem, just around how do you write the logic of what functions need to be run, and the dependencies between those functions, like what outputs of function A need to go into function B and C, etc., and how to handle that at this kind of logical layer. And then there's the isolation concern, where there are parts of this execution graph, this program that you're writing, that you actually want to run on different sets of compute, or you want to isolate them such that some nodes have permissions to some assets or some resources, databases, and others don't. And they're just pure mathematical functions, input, no side effects, and output. So, you have this kind of two layers where you write logic here, and there's another part that is responsible for provisioning the compute you need, handling the data flow, and in the case of agents, maybe providing some kind of sandbox compute that, now I'm bringing in some Kubernetes terms around pods. You can think of this as just like containers of a node that has a container that runs some program. So the pain shows up across these three types of use cases that are very common in the AI stack. I'm not going to go through all of them, but basically the point here is that concurrency and control over how these things are scheduled are very important in these three types of use cases. So as I mentioned earlier, the trap here is to reach for a DSL too early. You think like, hey, Python's great and everything. It's very flexible. It's dynamic. But now I need certain other things around compute provisioning and isolation. And I may even need to express some ideas that Python can't express. And I think my claim here is that actually Python can express all of this logic. What people really want is the ability to kind of write in Python or whatever their native language is and use some sort of configuration language that fits into the native language very easily, such that you can have finer grained control over the infrastructure. And now the cost of adopting a DSL are many, right? Like once you have a domain-specific language, you're going to have to learn the control flow constructs. You often get retry hooks that are basically like, how many retries you want to do and what is the exponential backoff logic, right? So you no longer have specific control that you may want to model in your specific domain around retry logic. And debugging requires some framework internals instead of your own code that you care about. And so with Asyncio Python, you can basically coordinating awaits is a language level problem, right? So coordinating what needs to happen when and what are the interdependencies, this is something you can write in any programming language. And now isolating compute is a system level problem. It's something that containers and analogous technologies can solve. It's just that typically we don't think of things as these two problems. We often have like a problem in between that is the intermediary language or grammar that you use to kind of convert your coordinating logic into things that actually run on some compute infrastructure, like a cloud like AWS or something like that. So just to hammer down the point, if I haven't already made myself super clear here, is that async IO is already part of your stack if you're using Python, modern Python at least. A lot of new frameworks and new patterns use async IO, or I think NEIO is another third-party library that makes concurrent programming in Python even nicer. Async IO is just the standard library that ships. And it's already kind of straight from the docs, something that is a perfect fit for IO bound and high-level structured networking code. And the missing piece really here is the container orchestrator piece. So when you back this language with container orchestration, you can also handle compute-bound code as well. And so I'll slowly get to this claim, but first I'll kind of talk about async IO for folks who are not super familiar with it, just like a quick background on this. So in Python, async programming uses an event loop. You can think of this as a collection of tasks that are waiting for things to happen. And so before GIL-free Python, and for many programs out there right now, it's still happening on a single thread. And so I'll get to try to explain this in a more intuitive way, but you can think of this as tasks happen, and as those tasks are waiting for things that are happening like at network calls or read-write like file system operations, it can yield the event loop to something else. So this task can kick off, it can wait for something externally happening, and while that's happening, while it's waiting, it can the thread can the event loop can kick off another task, and then another task, right, until all of them are complete. And so the way this looks in Python, if you're not super familiar, is you define you say async def, you define a coroutine. This is just coroutine is a thing that describes a piece of compute that you can run and do async operations on, and do concurrent operations on. You await on these coroutines. In this case, we're awaiting on async io.sleep, and so we yield back to the event loop. So we're saying, hey, I'm calling fetch. I'm yielding back to the event loop while this sleeps for 1 second, and so now the event loop can do other stuff. And async io.gather is a way for you to kick off there are many ways of kicking off coroutines, but async io.gather is a way for you to, in this case, call fetch multiple times on different websites. So fetch maybe like gets does some web scraping or something, gets the content of a URL, right? And so instead of doing fetch sequentially, you're doing them all at the same time concurrently. And finally, async io.run drives the event loop. So this is the thing that actually kicks off the program. So async versus sync. In this example, I've just like kind of re-rendered it here side by side. In synchronous Python, you do a list comprehension, and these would, in the simulated network call, we're just sleeping for 1 second, and this will run sequentially, so it'll take 3 seconds to complete. Whereas in async Python, this will take 1 second to complete, roughly speaking, right? Since these are all happening at the same time. So an event loop, as I alluded to earlier, is basically 2 collections. One collection is tasks that are ready to run, and then another collection is tasks waiting on something happening in the I/O or networking level. And so I/O and networking are Python delegates to the OS that it's running on. But this is a kind of a pseudocode schematic of what's happening underneath the hood in the event loop. But to give you like a more maybe intuitive sense of how this is, I'll show an example high-level example of how one would cook spaghetti, right? So just to give folks a sense of the difference between concurrency and parallelism, concurrency is when you kick off different processes and you're like waiting for stuff to happen, and while you're waiting, you can do some other stuff, right? So when you make spaghetti, you start boiling the water. That's going to take 5-10 minutes. While you're waiting, you may turn on some music and then chop some garlic and tomatoes. When you're done with that, you might start cooking the sauce, right? And as the sauce is maybe simmering, the water starts boiling, and then so you throw the pasta into the pot of boiling water. Sauce is still cooking, and you're kind of doing a handoff between like stirring these two things so that they don't stick to the pot, maybe, and they don't burn. And at the end, once they're both cooked, you mix the two together. So that's concurrency, right? You're not doing everything all at once. You're sort of kicking things off, waiting for things to happen, waiting for things to complete. And as they complete, you do the next thing in the dependency graph, right? So there's an implicit dependency between cooking the pasta and boiling water. Same with cooking the sauce and chopping garlic. And then finally, you can't mix the two ingredients until both are done. In parallelism, to stick with this analogy, you have 3 cooks and they create 3 spaghetti orders at once. And so inside of each of these red bars is each cook doing these 3 things. We can get fancy, right, by like having a shared pot of boiling water and shared like pasta that you just portion out, right? But in this simplified example, let's say they're just kind of cooking the spaghetti all kind of independently. So this is parallelism. So these two in Python land, this would happen with async IO, and then this would work with multiprocessing. Deep topic of things that I don't want to get into right now, but this is generally how you think about these two different but related concepts. So now I'll just go through like a whirlwind tour of all the different async IO constructs that are kind of relevant in things in general, but I'll kind of ground them to AI, ML, AI agents, ML, and ETL, right? So when you, and these are things you might encounter when you write your own agents or ML ETL pipelines, or if you're debugging stuff in a framework like, Flight itself or LangGraph or Pydantic AI, you may see some of this stuff, right? So in this case, we're making 3 parallel LLM calls, right? And we see async IO gather come up again. This is just a way for you to like gather all the promises, right? So a coroutine creates a promise. It doesn't actually create a value. Promise is a thing that will happen, the result that will be materialized at some point. And so you await this whole thing, and this basically kicks off all of the API calls, right? Just a quick side note that return exceptions allows you to have partial failure succeed, right? So this, even if one of these API calls or all of them fail, you'll still get a result. It's just that this collection of things now will have some of them with the actual LLM call results and some of them with some kind of exception. For structured concurrency, this kind of means like you want to scope child tasks. So you want to wait for all tasks within a task group to complete. So this is what the async IO.task group is. You create a like a context here with this task group context manager, and basically the rest of the operations here, this return won't progress until all of the child tasks underneath this are complete. And the use case for this, maybe you're building like a RAG-based vector database. For a RAG pipeline, you may need all the contents of the URL to be downloaded before you process them all in some downstream function. Semaphore is useful So this is like a kind of a rate limiting construct. So this allows you to limit the number of calls to fetch in this workflow to 8, right? So if you don't want to hammer, if you have 1,000 items you need to process, this will only call the LLM 8 at a time. Q is a different kind of construct for implementing backpressure. So in this case, I'm showing a hyperparameter tuning job where we create tasks. So these will immediately kick off model training jobs. And you have a set of workers that can do that. And in the queue, the model worker basically pulls stuff from the queue. And in this for loop, we are putting things in the queue. And we have a max size here of 200. And so we can only put so many documents in this case into the queue for the model training worker, or sorry, data sets for the model training worker to process at once, right? And so unlike the semaphore, this gives you a little bit more control over the logic of how data sets are placed into the queue, as opposed to this, which will just process the entire set of payloads with just like the semaphore as a gate to limit how many how many payloads come in at once. So yeah, these are all the things that I just mentioned. You have asyncio.timeout, so you can kind of take control over the timeout policy of your function calls, right? So here, we're calling some kind of external API provider. Maybe you're doing a tool call, and you're calling some sort of like web search engine or something else in your agent. This asyncio timeout basically allows you, the writer of the agent application, to bound the API call to 30 seconds. So if it doesn't return in 30 seconds, you'll have to have some kind of handling of it down here. So maybe you sleep for some amount of time and try again. Async 4, this is something you'll see if you look under the hood of any LLM library that sort of hooks into some of the LLM providers like Anthropic or OpenAI or whatever else, where you can kind of stream chunks in asynchronously using async 4. And so just to wrap things up in this section of the talk, basically like there's Python, right? All the things that you have with Python, like conditionals and for loops and while loops and try except. On top of typically what you would let a DSL orchestration tool handle for you around fan outs and retries and backpressure and queuing, actually, and timeouts, like Python has all of these things already. So the main reason why I would argue we don't use these things is because we have the impression that, okay, maybe there is a learning curve here to learning concurrent programming. And so that is a real constraint. But what I've been seeing in the ecosystem, at least in Python, is a lot more libraries are embracing async programming, either with asyncio or any of the other alternative third-party libraries like I think Trio or NEIO. And yeah, they're not even providing synchronous alternatives just because the core problem they're solving is around concurrent IO bound patterns. Okay, so hopefully I'm starting to get you here, so like async IO may be intimidating. There is a learning curve, but it's I would say pretty fun to learn, and just the mental models that you'll have to build up will also transfer to other programming languages that may implement things a little bit differently. And so now with that out of the way, let's get into like the need and how to think about containers as the isolation boundary for your AI, ML, and data applications. So what async IO can't do for you is provision GPUs, obviously. They also can't contain out-of-memory errors because, if assuming that you're in a single process, single Python VM, an out-of-memory will just blow up the entire thing. You can't isolate a noisy tenant from the rest of your platform. You can't scale horizontally without you rewriting the mental model. And so these are scheduler level, infra level concerns, not language concerns. So this is where some tools like Kubernetes can give you these hard boundaries. And so you get all the things, right, from a container orchestration. The thing you don't need to change now is your user code if you're following my kind of thinking and how to connect these two things, which I'll show you in a sec. Right, so async IO handles the logic, the coordinates, the function calls and the data flow. Pods are the things that are spun up to run pieces of your application, and configuration for how these two things connect are kind of like the missing piece that I'll show you in a second. Okay, so putting these two things together, I want to point to Flight 2, which is a Apache 2 licensed open source project owned by the Linux Foundation. It's been part of the Linux Foundation for, I want to say, 4 or 5 years now. V2, we've been building for the past year. There are parts of it that you can interact with locally and on a containerized dev box. We're actually going to GA next month, the whole platform. So we're going to open source the whole thing. But just to give you a sense of things, right? This is a pure Python implementation of like a simple batch inference workload where you have a predict function and you want to map over some certain of elements that you want to predict over. So this is pure Python. With Flight, you basically add import Flight, obviously, and then you add a task environment configuration. And what this does for you is it allows you to express your dependencies and also the resources you want your application to run on. So in this case, 2 CPUs and a gig of memory. You then add task decorators to basically let Flight know that, hey, these are actual Flight tasks that I want to run. You can also add some abstracted away logic here for retries, caching the outputs given the same input and given that the code hasn't changed. You could also implement retries like inside your Python code itself. And then you say asyncio.run. And if you do this, even with the Flight decorators and all that stuff, Flight gets out of your way. These are just run as regular Python functions, making this super easy to develop and debug locally on small data sets. Now to run this on Flight, you basically have to point it to a Flight cluster with flight.init and flight.run to kind of replace asyncio.run and give it some inputs. And so this will then run on a Kubernetes cluster. You can also just run this locally. So if you say flight run --TUI, we also ship with a really nice TUI. And this, again, just runs as pure Python. But this gives you all this. You can kind of start seeing like Flight handling some of the I/O for you just on your local Flight file system. Right? You can see we passed it some data, 5 data points, and it kicked off 5 predict runs. You can also start a dev box, which I'll show you later if I have a little time. And Flight works really well with UV. You can say UV run, and you can run the same script that we just saw earlier. And this will run on a dev box. The dev box runs on a Docker container. So you need Docker installed on your laptop. And when you say Flight start dev box, it'll spin up a little mini Kubernetes cluster with all the different dependencies that Flight needs, mainly Postgres and a S3-like blob store and a UI. And this will just run locally but you can get nice observability around what ran, what the inputs and outputs were, what the logs were, things like this. Okay, so I've given you like the developer experience, how you would write Flight, but I think it's worth diving a little deeper into the architecture of it, just so you can see what parts are doing the sort of Python async IO bits and what parts are the container orchestrator bits. So at a high level, you just write, as you saw, Python functions with some Flight configuration around, the decorators, right? Where these things run, how they run, what dependencies they have. And if you run it locally, as I said, as you saw on the TUI, this just runs on a local Python process, works with your local file system to do the IO stuff. But on a dev box and on an actual Flight cluster, this is actually running on a K8 or K3s cluster, where the run entry point is the thing that kind of orchestrates the rest of the actions, right? So we call the main thing entry point a run, the things underneath it actions. These were the predict function that you saw. And this actually automatically handles serialization and deserialization to and from an S3 MinIO or RESTFS blob store. And so the examples I showed you are a little simple. We can take a look at a more involved one a little later, but really this is what's happening under the hood. Is Kubernetes is spinning up the compute you need, and then Flight is managing this sort of on top of Kubernetes, as well as managing the passing of data across the different tasks, the different runs and actions. And so with that out of the way, I just wanted to like revisit the async stuff that is implemented in the Flight Python SDK, and sort of just point out, we don't have to read all this stuff, right? But we learned about queues and task groups. So Flight actually does use this under the hood. We learned about handling errors and slowdowns, and implementing backoff re-enqueuing logic here. So we're using the queue here to handle errors at this level of retries, right? So if the task fails and it was due to some intermittent network failure, it'll retry and see if it succeeds. And this controller construct is the thing that handles how runs and actions work. And again, this all is using just plain Python that you can debug. Now for per parent, a thing that a parent does is a parent task, a run does is it kicks off a bunch of things, right? So this remote controller that inherits from controller is the thing that uses semaphores, async rate limiter, a construct that I didn't cover. And this is the thing that coordinates how things are kicked off and limited so that you're not blowing up your Kubernetes cluster. And so the logical execution path is you write and then run your async IO tasks. These are submitted to a driver loop, which is again like that main driver function that coordinates everything else. This is then sent to the control plane. You can think of this the Flight control plane that manages and sees what work needs to be done, what's completed, what's incomplete, how to kick things off. And then you have a container runtime that when Kubernetes spins up a pod, a node, and pulls down a container to run it on, to run your code on, the control plane manages this. Once the container is done, you're not just wasting money or time on idle compute. It'll spin this down for you. The control plane will also make sure that all the state and all the data, which in some cases actually it'll never see. It'll just see that in your process, some files have been written to that need to be written to your blob store. And then this goes back all the way to your Python task, which then says, okay, this task is complete. Let me move on to the next one. And so there are some trade-offs, obviously, with any kind of thing that you build with this kind of large dependency on a container orchestrator. There's some trade-offs from a Python perspective, right? So in Python, you can't actually have global variables in the top-level scope of your module, right? So this global state you'll have to manage on your own with something like a key values cache, like Redis or something like this. Function calls in terms of flight tasks are no longer cheap. So there's a bunch of network and serialization and deserialization that happens because you're no longer working in memory between flight tasks. You're working across containers. And so you have that blob store layer in between and all of the things that entails. And then finally, you have a single failure domain. So partial failure and retries at workflow scope. So Asyncio helps you express fan out and all that logic, but it doesn't remove distributed semantics. You still have to like think about that when you're writing your code. But hopefully, as you've seen, there's a huge benefit to kind of taking on this additional dependency on container orchestration, where you can actually scale your workloads, whether they're agents or ML workflows or ETL pipelines. You can scale them up arbitrarily, constrained by whatever your container orchestration or cloud can handle. So to put it all together, we'll make a peanut butter jelly sandwich making agent. Not a real one, of course. But we'll see that here we're going to use Anthropic to create this agent. So we're going to use Claude model under the hood. We're creating our task environment here that our agent's going to run on, has secrets, just minimal resources. And actually, Flight works really well with UV. So you can actually create these single isolated standalone Flight scripts that just picks up the dependencies. So you can call this with UV run. Next, we define a bunch of tools. So all the tools we need for a PBJ sandwich making agent. Then we make the agent itself. So these are all just tasks, right? So these are just functions. This is no framework really here to speak of. Really, the only thing here is like abstracting away running the agent on some prompt and with some tools and a given model. So here, we define the tools, feed them into the agent. We can fan out just with regular Python if we give it multiple goals, right? And then finally, we use our if name equals main conditional block to just run the thing. Here we're giving it 3 goals to just make a peanut butter sandwich, a PBJ sandwich, and just a jelly only sandwich. And then when we run this, I'll run this in a second. We can see that concurrency is actually being handled by the sandwich agent. So this is the logic of the driver task that's kicking off all these subtasks. And we can see that the subtasks, the sandwich maker actually it's constrained by the laptop that I'm running this dev box on. But as best as it can, it's actually concurrently working on the sandwiches separately, or each step that can be run separately at the same time, right? So it's making each sandwich at the same time, getting bread at the same time, right? And so this is basically concurrent programming plus isolated containers sort of running seamlessly together. And so real quick, I just wanted to show you in action this last agent. So I have a PBJ agent over here. This is all the code I just showed you. Just gonna go ahead and run this on my local dev box. Let's hop over here. And yeah, this is just the GIF I was showing, right? Each of these flight groups, this is just a way for you to kind of group together related tasks. You can see inputs and outputs. Mainly these tasks are just producing outputs. In the end, you have a assembled sandwich for each of the sandwiches, and you have your ultimate output here, which is just some flavor on top of this kind of toy example. But you can see that if you have an actual meaningful agent that you're building, you have access to all of the Python programming flexibility while getting immediate concurrency and parallelism on separate machines. So that, for example, if this particular step blows up, Flight will actually pick up from where it left off without rerunning all the other steps that succeeded. And cool. So basically, call to action is, if you really want to fully use, debug, or understand any of the internals of these very, very popular libraries, they all use asyncio or some variant of it in their code base and even in their user-facing APIs. And so really, I just encourage you to take a look at it if you haven't already, or if you're not super familiar with it. I think it'll pay dividends moving forward. And so tomorrow, when you have this use case of like, hey, we've built out our pipelines locally or in our notebooks, now we need to like productionize it. Now we need to scale it up. Before reaching for a framework, DSL, static DAG tool, learn a little bit about asyncio. Learn about some of the constructs here that I've reviewed today. The code stays reviewable by both you, a human, and agents. And secondly, don't confuse the need of I need compute isolation and isolated boundaries around steps in my application with the need for a DSL. The DSL is just kind of the means to an end to achieve these things. These things being provisioning compute and containing out of memories, having multi-tenancy so your team can like work on shared resources. So these are all container orchestrators. These are all like a container orchestrator's job. And maybe it turns out that the best DSL for AI was right in front of you all along, whether that be Python or whatever language that you're familiar with. You just need to go ahead and implement what I showed you that Flight implements, bind your programming languages function calling and concurrency semantics with something that provisions compute for you under the hood. And with that, just want to thank folks for their time, people who showed up. Finally, just a quick shout out to Try Flight DevBox. I should probably also just have the URL here actually, which is over here. You can try it over in running on the dev box. Pretty quick, easy setup here to just get it running locally. Start running an example. All the code that I'll show, I'll share on LinkedIn a little later. And with that, yeah, just wanted to wrap this up and hang around for a little bit if folks have questions.
There are a couple questions. I don't know if you can see the chat.
Oh, weird. Oh, wait. Sorry, I was on the wrong tab. I'll start from the bottom and go up. Can you get to your slides? Absolutely. We will be sharing your slides. How do you test your workflows? Yeah, I mean, as you saw, just because it's Python, with some caveats, most of the code you'll ever write with Flight will work locally. Obviously, that the caveat is like if your workflow relies on a GPU being available, you will locally need to also have a GPU available. So you can have a few conditionals here and there for like if you're using PyTorch, for example, you could use the underlying Apple silicon, I think, with MPS backend. So you'll just have to write your code to be sort of portable in that way. But yeah, generally testing workflows is super nice because everything is just a Python function. So you can test your flight tests independently, unit test them with PyTest, all that good stuff. It's great. How to deploy a coordinator that actively coordinates tasks. Yeah, I mean, the general answer to that question is kind of, I'm not sure if I can immediately answer, but the power of Flight actually is that the coordinator is basically your main function, which is also itself a task, right? And so in Flight 2, we got rid of this concept of workflow. Now workflow is just a colloquialism that we say to mean a thing that runs multiple steps, that composes other smaller atomic things. But yeah, you hear, right, after computing all these things, I get the mean of my predictions. I could do other stuff here before returning some other result, right? So when we look at the UI and just like the execution graph, one way to answer your coordinator question is that this is now the coordinator. Another way to interpret that question is there is a whole system that I'm not a platform engineer. I'm an MLE AI engineer, kind of in background. So a coordinator can also mean the control plane components that I think in Flight are written in Go that bring containers up and use the Kubernetes API and also just our custom logic in Flight to figure out where to send jobs, how to spin things up and tear things down. So that's a whole can of worms that I'm not really an expert on, but that's roughly how it kind of works in the back. I try to cover it slightly over here in this timeline diagram of just like where things happen and where things are, what parts of the system are doing what. Claude 6 will make you lunch. Yeah, we'll need to bind Claude 6 to a robot and have it make some sandwiches. Cool. Are there any easy to implement agents you have built that have great ROI for devs? Oh, that's a great question. It's the dev tooling agent space is very saturated just in terms of like things you do locally. Obviously there's Claude Code, Codex, OpenCode, and Pi. There's nothing that we have built to add to that space, I want to say. The things we're building right now actively in agents, and I think it's something that's a little harder to penetrate in terms of market, in terms of the market, are long-running, long-horizon background agents that sort of run on your compute infrastructure that do useful things. So I can point you to some stuff we've built at Union, which also will mostly work in Flight, just around deep research. We have our own take on we've implemented, Andre Karpati's auto research agent here. We have a coding agent. None of these, though, we've really deployed and are using internally. The things we've deployed and are using are kind of specific to our business at Union.ai, right? So these are things like we have an agent that changes node pool configurations under the hood. We have agents that can sort of triage customer questions. Most of them are human in the loop, though. So we have nothing yet that directly interacts with customers, just because we need to be more confident in how well they do. Okay, cool. Thank you. We are at time. Thank you for all the questions. Again, we'll be sharing the slides and the material following up here, just probably as a comment on the LinkedIn post. But yeah, thanks everyone.